This is the second video in the coupled oscillator series. In addition to the first video, you should also watch the video on eigenvalues and eigenvectors in order to be familiar with the techniques that we're going to use in this video. In the last video, we studied this problem of two cards connected with three springs to two walls. This is essentially two different oscillators. Card 1 and card 2 can oscillate independently, but they are connected together. And when you write down Newton's second law for the system, you get the system of coupled differential equations. Using this matrix notation, we were able to write these equations on a much simpler form, which suggestively looks very much like that of a single simple harmonic oscillator, except that it uses matrices instead of scalars for m and k. We then also applied this ansatz for the solution, saying that the solutions are probably periodic functions, and that led us to this form for the equation that we need to solve in order to come up with the complex amplitudes, which contain both the actual amplitude of the motion as well as its phase shift. And if we do this, if we solve this, we should be able to get the full solution for the problem. We can get the position as a function of time just by taking the real value of z here, which is written as a complex exponential. So let's compare these results to the eigenvalue equation. So for eigenvalues, we know that if we have an n by n matrix, which we're going to call A, and we multiply that by V, if V is an eigenvector, then that gives us an eigenvalue lambda times V again. And we can rewrite this, as we showed last time, as A minus lambda times the unity matrix, or the identity matrix, which multiplies V equals 0. And then the solution for this can be found, the eigenvalues can be found by taking the determinant of this vector that multiplies V, matrix A minus lambda times the unity matrix equals 0. And this last equation is known as the characteristic equation of this eigenvalue problem. Now, this equation here, A minus lambda 1 times V equals 0, looks similar to, but not exactly like the equation for the coupled oscillator. We can make it look, if you like, exactly like it by simply multiplying this equation by m to the minus 1 from the left. So m to the minus 1, of course, the inverse of the mass matrix looks like that. And when it multiplies the mass matrix, you just get the unity. So therefore, this equation becomes and that looks exactly like this equation. So now, in order to find the eigenvalues, which in this case is omega squared, we just take the determinant of this. So we obtain that determinant of m to the minus 1, k minus omega squared 1 times 1 equals 0. Now, the determinant of a product is just the product of the determinant, so this is perfectly equivalent to saying the determinant of m to the minus 1 times the determinant of matrix K minus omega squared m equals 0. And then we can just cancel that out because it's never equal to 0. Okay, this is now the equation that we are going to solve here. What we obtain, I should use black. When we solve it, what we obtain are the various omegas that correspond to whatever solutions there are here. There might be more than one omega, so there might be omega 1 and omega 2. These are known as the normal frequencies. And then from there we can solve for these complex amplitudes, and they describe the motion, and they're therefore known as normal modes. So we have now outlined what we need to do. Next, we will apply this to a specific problem. The problem that's described here in this figure is slightly more complicated than it need to be, so we will simplify things slightly. So let's solve the specific case of all the masses being the same. So m1 equals m2 equals m, as well as k1 equals k2 equals k3. And then we obtain that the mass matrix will simply look like this. Just m's on the diagonal. And the K matrix like this. 2k, k minus k, minus k, and 2k. By the way, both k and m are symmetric. That's true over here as well, but here it's more clear. Since they're both symmetric, we know that the eigenvalues are real, which is a good thing, because frequencies are real. And we also know that the various a's are orthogonal to each other. As we'll see, that's something that can be quite useful in order to test whether the solutions you obtained are reasonable or not. Okay, so let's now go ahead and solve for the actual eigenvalues of this problem. And in order to keep track of what we're doing, I'm going to retain the picture here, but we're going to have to change a few things. All the masses and all the k's are the same. Okay, now we all have to do is take the determinant of this matrix over here. So we want to calculate the determinant of k minus omega squared m. Okay, so if you just look at the form that k and m take, that becomes the determinant of, on the first row, we have 2k minus omega squared m, as well as minus k. On the second row, we have minus k, and then 2k minus omega squared m on the second row, and that has to equal to 0. And then we can just take calculate this determinant, and here's what we get. And then we can cancel out this k squared here against 1k squared over there. And that becomes a quadratic equation, quadratic equation in omega squared, which you all know how to solve. And if you solve it, you will find that essentially you get k minus m omega squared. Not essentially, you get k minus m omega squared times 3k minus m omega squared equals 0. In other words, we get two solutions for the omega squareds. We get that either this first parenthesis is 0 or the second parenthesis is 0. So we get two modes, or two normal frequencies. Each corresponds to a different mode. So we have that either k minus m omega 1 squared equals 0. So that means that omega 1 equals the square root of k over m, or we get that 3k minus m omega 2 squared equals 0. So this is now that omega squared equals square root of 3k over m. Collectively, these two now are known as a spectrum. of the problem. A spectrum is a collection of frequencies, and that's what we have here. We have the two different frequencies at which the system can oscillate. It can oscillate either at omega 1 or at omega 2. We see that they're different. We have one looks like the normal harmonic oscillator, and then the other one looks a little bit different. That's supposed to be a K here, if that wasn't clear. The next thing to do, now we determine what the frequencies are, is to determine what the normal modes are, what the amplitudes. How do these guys actually move? We know what frequencies they're moving at, but how do they actually do it? What does the actual motion look like? So for that, we now just calculate K minus omega, and we take the specific omegas that we are working with, omega 1 or omega 2, squared times m, and this multiplies A, and that has to be equal to 0. So let's start with omega 1. We get now that K minus omega 1 squared vector m, matrix M equals just by substituting this value for omega 1 into this equation. And that then becomes just a matrix which is K minus K minus K and K. So that's just K times the matrix 1 minus 1 minus 1 and 1. Okay. So that's what this looks like, and then we just have to multiply that by A, so it gives us that and this is now two equations, A1 minus A2 equals 0, and minus A1 plus A2 equals 0. And both of them give the same result, that A1 equals A2. They have to be the same, actually. This matrix, K minus omega squared times M, is a singular matrix. So therefore, this is an underdetermined system. So it can't be two independent equations. They're dependent on one another. And that's another way you can check whether the result you get is reasonable. So this first normal mode is characterized by the fact that A1 equals A2. Now, A1, of course, is the amplitude times e to the minus I delta 1, and A2 is A2 times e to the minus delta 2. What we're saying here is that both the amplitudes and the phases are the same. They're moving in the same direction. So A1 equals A2 equals A, and delta 1 equals delta 2 equals delta. This then means that Z is equal to, both amplitudes of Z are A, and e to the I omega t minus delta, and from there we can calculate x, the actual position. We know that x of t is just the real part of z. So we get then that x1 equals a cosine of omega 1 t minus delta, and same thing for x2, like that. So that's a solution for mode 1, the one that's oscillated frequency omega 1, and then we just have to do the same thing for omega 2. So we'll start by just erasing this stuff here. So for omega 2 is square root of 3k over m, so omega 2 is just 3k over m. That means that k minus omega 2 squared times m is just equal to that. Which then becomes this matrix. And the final result then is just k times the matrix minus 1, minus 1, minus 1, and minus 1. Okay. So this equation here then, for calculating the mode, is just 1, 1, 1, 1 times a1, a2 equals 0. We're divided by minus k. So that's the same thing as saying that a1 plus a2 equals 0, both in the first row and the second row. I'll differently put a1 equals minus a2, and that I can call a e to the minus I delta. Okay, so this means then that z, in this case, z2, if you will, is equal to a minus a e to the I omega 2 minus delta. Okay, so that's the solution. We take its real part, using the fact that a1 equals minus a2, and we get here now that x1 equals a cosine omega 1, omega 2 times t minus delta, and x2 equals a cosine omega 2 t minus delta. So those are the two solutions. We have mode 1 and we have mode 2 with different frequencies and different modes, I'll describe it thusly. So now I'd like to illustrate what these two modes actually look like. So here is the system. Now I didn't find any animations that looked exactly like this, but we have here an animation that is very similar and in fact mathematically equivalent. It's two pendulums attached by a single spring. The two outer springs in this case is in this animation here, that role is played by gravity. It applies a restoring force that brings the masses back towards their equilibrium. And for small motions of the pendulum around its equilibrium, it's linear, so mathematically it amounts to the same thing. So this illustration here, or this animation here, shows the movement of mode 1. So you can see both masses are moving in unison, left to right, and the spring that connects the two is not extended or compressed in any way. The second mode looks like this. So here it's the other way around. The two masses are now moving in opposite directions. Their amplitudes are the same, but they're moving 180 degrees out of phase, or with amplitudes that have opposite sign that amounts to the same thing. And now we get a large compression and contraction of the spring that connects them. So that's what they look like. Now, those are the two modes. But if you want to write the motion in its most general form, you have to take into account the fact that the system can have both modes excited at the same time. So this means that we have the general solution. Looks like this. We have x, so vector x, as a function of time. We have first mode 1, so it has amplitude 1, and the two amplitudes are in phase of cosine omega 1 times t minus delta. And we add in the amplitude of mode 2, and now the two amplitudes are completely out of phase, times cosine of omega 2 times t minus delta. And that's the That's the most general form of the motion of the system. The final observation I'd like to make here in this video is that if you look at the two modes, we have mode 1, there's A1 and A2 equals A2, and in mode 2, A1 equals minus A2. We have that A for the first mode, equals A times some phase, and for the second mode, they're equal to A minus A times e to the minus I delta. If we then take these two vectors and take the scalar product, right, A1 scalar A2, that gives us A squared minus A squared times e to the minus 2 I delta, and that's 0. So these two modes, mode 1 and mode 2, are orthogonal to each other, or normal to each other. That's the reason why they are known as normal modes, and that's also yet another thing you can do in order to check to see if the solution you've obtained is reasonable or not. All right, so I'd like to end this video by leaving you with two questions. And I'd like you to think about those two questions and see if you come up with the answers by the time next lecture comes by, which is when I will ask them in class, and hopefully some of you have come up with good answers. So the first question has to do with the value for omega 1. Omega 1, that frequency is the same as it would be if we didn't have the middle spring in place. Basically, it's the frequency of a single cart of mass m attached to a single spring of spring constant k. And this happens even though we have this complicated system. So why is it that for mode 1 it seems that the frequency is the same as for a simple harmonic oscillator with just one dimension? Is that an accident, or is there a deeper reason that you could pinpoint? Second question is, what would happen, do you think, if I held cart 2 stationary, perturbed cart 1 from its equilibrium position, and then let go of it, and start a system oscillating from that point? What would be the behavior of the system? What would the motion look like? So that's the end of this video. Thank you very much for watching. And next time we'll treat another example, essentially very much like this one, that is very important in many areas of physics. That's the case of the weakly coupled oscillator when this k here is very small.